Now, as you see from the title on the screen, we're going to be talking about logarithmic functions, and then eventually their relationship to exponential functions. But before we discuss logarithmic functions, we want to discuss what an inverse function is, because a logarithmic function will be an example of such an animal. So let's look at inverse functions. And in order to set the scene here, let's observe something about a familiar function that you know. The familiar function that I will look at is f of x equals x squared. And this will repeat some of what we saw back in the one-to-one function segment. But it's worthwhile to re-look at this. This is an example, as you recall, of what I named a many to 1. Actually, I think I said more than 1x to 1f of x. This is a many to 1 situation. So if you're looking at a function in the form of my little function machines here, then what we've got is a situation where we have a function that might take in 2 or minus 2, for example, and produce on the other end the same number 4, because 2 or minus 2 when squared is 4. So this is a function that is our f of x function here, and it's a squaring function. Now notice this is not reversible, as I said there. If I start with 4 and I go backwards and I ask where did this come from, there's no way to tell. There are two possibilities, so going backwards is not a function. Not a function in reverse. Okay? And another way to look at this, of course, is to look at the graph. So let me draw that here because we want to have both images in our mind. The graph of f of x equals x squared, of course, is this parabola, which we know well. And here, say, is 2, and here, say, is minus 2. And we know that they both go to the same height on the graph, the height 4, which is their f of x value for the function f of x equals x squared. The problem, of course, seems to be that although we can go forward, take the x values up to the y value and have no contradiction, we have a legitimate function. Going backwards is the problem. So it seems to be, if I try to analyze this, that the problem seems to be if I have x1 not equal to x2, then I've got them both going to the same y. That seems to be the problem I'm facing here. That's what makes this not reversible. Well, of course, that is exactly the kind of problem that is overcome by a one-to-one function. A one-to-one function doesn't have that. So we see that a one-to-one function, which doesn't have any of the problems of non-reversibility we saw before, a one-to-one function can be what we might say is undone. It can be undone. Let me give you an example of what I mean by that. Here's a nice example. G of x equals 2 times x, and I'll say that that is undone by h of x, which is 1/2 x. Now, that makes sense when you think about what these functions mean. This is the doubling function. This is the halving function. So if you first double something and then halve it, you're back where you started. And in reverse, if you cut something in half and then double it, you're back where you started. So the kind of picture you might have here, if I'm allowed to draw a little picture here, imagine we start with x. We apply g to it, so g of box is 2 times box. We end up with that, 2x at the end. And then if we continue the process, we take 2x and apply h of box, which is 1/2 of box 2, 2x. What do we end up with? We end up with 1/2 of 2x, which of course is equal to the original x. So we've gone forward, and this was 1, 2, 1 going forward, and the reverse is also 1 to 1 going backwards. So maybe we have a little bit of an aha moment here, and we have a pretty good idea of what sorts of functions are going to be reversible. So I think it's time to write down a definition of what we'll call an inverse function. The word inverse is used and not reverse, but that's just a piece of terminology we can get used to. Definition: the inverse of a function, say f, so the inverse of a function f, and it'll have its own notation. It'll be denoted f inverse, a little -1 up there, and we'll talk about that in a minute, is a function such that, and here's the definition, such that, this is the key point, if you take f inverse of f of x, so what's happening here? F of x is being applied to f, and then f inverse is following that application. You end up back with x, where you started. And if you start with f, and if you start with f inverse rather, the middle one, and then go outward and do f, you end up back with x. Now this is the key idea here. So I'll even put key here up in the corner. That's the key idea for an inverse function. Now we have to be a bit more specific. Since f is the function that's starting this composition here, the x's that come out, this is going to be for all x in the domain of f. The domain of f where f begins. But if we look at this previous example, we begin to notice something. This x over here on the left is a member of the domain of G, isn't it? Because it goes into G. Also realize that on the return it becomes a member of the range of H. And that is in fact always true. So this is true for all x's in the domain of f, and the domain of f will be the same thing as the range of f inverse. And likewise here, if you start with f inverse, that means this is true for all x in the range, or rather the domain, let's start with that one first, the domain of f inverse, and that will be the range of the original function f. So with that definition in mind, let me go ahead and draw a little bit more elaborate picture down here. Imagine that we have two sets here. This will be the domain of f, and here's a point x, and x will be acted upon by f and result over here in a little point f of x. That's what functions do. Now this will then, of course, in that case, be the range of f. But now, if I want to act upon f of x via a function inverse, f inverse, this now becomes the domain of that new function f inverse, and this becomes the range of that new function f inverse. And what do I have here? I have f inverse of f of x, which of course is equal to x. That's exactly this statement right there. So the range of f and the domain of f inverse are the same. The domain of f and the range of f inverse are the same. They're just reversing, that's all. Not a mystery. So this is the definition of an inverse function. What sorts of functions have inverses? Here is the question, the answer to that question. Fact: if f is a one-to-one function, that's based on all the work we just did, if f is a one-to-one function, then f inverse exists for f. So f has an inverse function that undoes it if it's one-to-one. That's automatically true. Now, I said I'd give you a little bit of warning about the notation. Let's do that right now so we can get that out of your system. Notation warning. First of all, f inverse is read, as I just spoke it, f inverse. There is no other way you should be reading that. And let's be clear, this -1 up here, although it means inverse, it also has another meaning you may recall. But in this case, f inverse is not the same thing as 1 over f. Not true. Okay? Do not use that. When an f inverse, when the inverse is used, the -1 is used in the context of a function, it means the inverse function. It does not mean 1 over f. So be a little careful with that. Okay, well, let's look at a couple of functions that are inverses of each other, and let's just verify. just to get into practice here. Verify 2b inverses. Here we go. Suppose we take the function g of x as x cubed and take the function g inverse of x. Of course, I'm claiming it's g inverse of x. I think you'll believe me, though. It's the cube root of x. Okay? And to verify that these are inverses, what must I do? I must check that if I apply g and then g inverse, I end up with x. If I apply g inverse and then g, I end up with x in either case. So, let's start with the first one, g inverse of g of x. Now I'm doing this to remind you of all of those composition exercises we did long ago back in Unit 2. G inverse, then what is g of x? Just copy down, g of x is x cubed. And now as you remember, this is where you have to think about what this means. So it was wise to rewrite g inverse here as g inverse of box is the cube root of box. And now I want to do g inverse of x cubed, so I'll place the x cubed into the boxes, and I'll have the cube root of x cubed, and as we know, that's x. So it does work one way. And this helped us here. Going the other way, g of g inverse of x, well, g of g inverse of x we just copy is the cube root of x. And then I want to apply g. Again, it's probably wise to think of this as g of box equals box cubed. And then I'll take that idea down here. The box is going to be filled by cube root of x, so this will be cube root of x cubed. And of course, that also is x. So I now have verified that no matter which way I apply these functions, they undo each other, and therefore they are inverses of one another. Well, I think you should do an example like this, just to get your algebra and composition juices flowing. Here is the function. Verify to be inverses these two functions. F of x is x minus 5 over 2x plus 3. And g of x is 3x plus 5 over 1 minus 2x. And if you remember what I just did on the problem I showed you, I used the boxes to help me tease apart what I needed to do at each stage. I recommend that you do that here. I'll come back and show you what I did. All right, let's see what I did on this problem. Now you see what I already did. I knew that the boxes ideas would help me, so I rewrote both of the functions with boxes in them. Now I'll go ahead and see if they are inverses of one another. First I'll try f of g of x. In that order, f of g of x, of course, is this with x's in the place of the boxes. So that's f of 3x plus 5 over 1 minus 2x. Now that's the easy step as usual. The harder step is the second step, where I need to put this object here in for the boxes from f of box. There'll be a box there and a box there, so I have to be a little careful about that. 3x plus 5 over 1 minus 2x minus 5, and that's all over the much larger bottom, which is 2 times 3x plus 5 over 1 minus 2x minus 3. Okay, and actually, let me see. 2 box plus 3. I'm sorry, that's got the right function there. The original function I just checked is a plus, so let's put a plus in there and make sure that's right. Okay, this is a very large fraction. I have, as I see, fractions on the top and the bottom with the same denominator. One slick way to get that denominator out of there is to multiply top and bottom by 1 minus 2x. So that will knock out this denominator and this denominator. Of course, they will multiply by 5 and 3, but at least I won't have any more double fractions. So what do I get out of this? 3x plus 5 minus 5 times 1 minus 2x, all over 2 times 3x plus 5, plus 3 times 1 minus 2x. Just multiplying everything out. And with a little bit of work here, we see that we've got 3x plus 5 minus 5 plus 10x, multiplying out everything on the top, and 6x plus 10 plus 3 minus 6x on the bottom. Well, what happens here? On the top, 5 and minus 5 add to 0. 3x and 10x add to 13x. On the bottom, the 6x and the minus 6x add to 0. 10 and 3 add to 13. 13x over 13 is x, and so, in one direction at any rate, f of g of x equals x, so it looks like these might be inverses. But you need to check both directions. You cannot just check one. So let's check the other direction, g of f of x. Now recalling the f of x from the previous page, that'll be g of x minus 5 over 2x plus 3. Okay, don't want to lose my plus this time. Equals, and now I remember what g looked like. G looked like this. So I want to put in my expression into 3 box plus 5 over 1 minus 2 box. It's easier if you have this all on one page. 3 times x minus 5 over 2x plus 3 plus 5, all over 1 minus 2 times x minus 5 over 2x plus 3. And again, I'll use the same idea to simplify. I'll find out the common denominator here is 2x plus 3. Multiply top and bottom by that. That will now yield, if I multiply everything out on the top, 3 times x minus 5 plus 5 times 2x plus 3. And on the bottom I'll have, remember the 1 has to multiply by the 2x plus 3. So I get 2x plus 3 minus 2 times x minus 5. Well, multiplying everything top and bottom, I have 3x minus 15 plus 10x plus 15. On the bottom, 2x plus 3 minus 2x plus 10. And once again, things simplify nicely. The minus 15 and the 15 add to 0. The 3x and 10x give me 13x once again. 2x and minus 2x add to 0. 3 and 10 add to 13, and lo and behold, I have x again. Since I got x in both directions, g f of x and the previous f of g of x, the two functions are in fact inverses of one another. Now, we won't be spending a lot of time doing this. I wanted to do this so that you would get a reminder of some of the algebra we did earlier in the course, which will be helpful, and how to deal with compositions, which will also be helpful. Okay, there's one last thing we need to talk about before we leave the topic of inverses, and that is graphing f and f inverse. Okay? We need to learn how to graph these two. And here is the basic idea. If you start with A and you apply f to A, we've seen this picture before, you get f of A. Then if you apply f inverse to the f of A and go backwards, you end up with f inverse of f of A, of course, and that is A if these are inverses. So another way to say that is, if A f of A, that point is on the graph of f, so that'd be the point A f of A would be on the graph of f, then the reverse, f of A is on the graph of f inverse. Because if I go backwards, f of A becomes the domain element and A becomes the range element. So that makes it very easy to produce a graph. Let me show you how this looks in general with a nice picture. Hope this works out well. Here is my y-axis and here is my x-axis. And let me mark in here, and you'll see why in a minute, this y equals x 45-degree line. Okay? So I've got that marked on there. Now, let's mark a few other points. Let me imagine that A is here on the x-axis. And then when it goes up to the curve, wherever the curve is, this is the height f of A. Okay, so that A goes up there, and this is a point on the curve. Okay? Now, that is then the point. Let me label it here. This is the point AF of A. All right, from what I just said on the previous page, if AF of A is on the curve, y equals f of x, then the inverse curve has the point f of AA. So let me come down here and mark a point, let's see, right about there. That would be f of A. And when we go up to the curve, it will go to a height of a. So it will have this kind of picture, and this will be the point f of a, which lies on the inverse function curve. So there are the 2 points. And this is the y equals x line in between. And if I continue the dots out here, you see that they intersect. This point here has height f of a. It also has x value f of a, so it is on the y equals x line. Because remember, the points on this line are all of the form xx. Same thing here. This is the point AA. So we've got this little square here. And the opposite ends of the square are the points that lie opposite each other from the original curve to the inverse curve. In fact, they lie on this diagonal, and they are exactly at right angles to the y equals x line. So this is an observation that will allow us to draw the inverse curve if we know the original curve. If the original curve looks like that, we're going to know that the opposite curve, the inverse curve, looks like that because it's a reflection. There's a reflection here across, instead of the x or y axis, across the y equals x line. Now that's very different from what we've done before. We usually reflect it across the x or y axis. Now we reflect across this line to get the difference between an original functions graph and the inverse functions graph. So let me put that down in the form of a theorem and clean this picture up a bit. Now that I've seen the analysis, I can just write down the graphs. Here's the theorem. The graph of, or the graphs of, f and its inverse, f inverse, are, and here is the fact about them, they are symmetric across the y equals x line. So that is the connection between the graph of the original function and the graph of its inverse, which means if you know the original function and you know its graph, you can immediately draw the graph of the inverse without plotting any points. So here's the idea once again, that if you have your x and y axes, and this is the y equals x line, there's the x and y axes, and this is your original curve, say something like this. If this is y equals f of x, then I immediately know that the graph of the inverse function looks like that. Y equals f inverse of x. And I did that by simply reflecting across this line, so that a point AB here becomes directly across at right angles to this 45-degree line, becomes the point BA on the inverse functions graph. So this is it. A reflection across the y equals x line is how you get the graph of the inverse function. Very nice, very straightforward. Well, with that, we finish our information about inverse functions in general. And now we're going to go on ahead and look at a particular one, the logarithmic function. Now it's time to look at specific inverse functions. And since the title at the top says logarithmic functions, you might expect that that's what we're going to look at, and so it is. Logarithmic functions and their graphs. So let's go ahead and get right to that. Recall, and this will be the connection to exponential functions, recall that since f of x equals a to the x, remember the exponential function we looked at, and of course I'll just remind you that a is greater than 0 and a is not equal to 1, usual fact about the base. Since that function is 1-to-1, as we discovered earlier, it has an inverse. So an inverse exists for this function. And we're going to give it a name. And here we go. Definition: the logarithmic function, and we'll put in parentheses here to the base a. You'll see where the a comes in. The logarithmic function to the base a in standard form is the following. Y equals log subscript base A of x. I'll talk about the notation a little bit in a moment, but log, it's a subscript down here, A, and that's where the base goes. And the object you're operating on, the domain element, goes here. The parentheses are not always necessary, as you'll see. If there's a single object there, it's often left out. But I think you should use it most of the time. And what is, I mean, that's just the name of it. What is it defined to be? It is defined to be the inverse of f of x equals a to the x, the exponential function with that base. So this a down here is what we're calling the base here, just as we called the a for a to the x, the base for the exponential function. And so we've given the name log base a of x to a to the x's inverse function. We're not using that inverse notation we saw for inverse functions. We have this special name, log base a. So we'll have to get used to how to play with this and manipulate it. So to put things down, we have the following statement that y equals log base a of x. That holds if and only if x equals a to the y. In other words, they undo each other. And another way to put that is the following, that a to the log base a of x is simply x. Now see, this is unusual. This is not the f and the f inverse sitting next to each other. What we seem to have here is a risen to the power log base a of x. So we have an exponentiation going up because of the peculiar nature of the exponential function, that it writes things upward. But when you apply these two functions in order, you get x. And if you do it the other way, if you do log base a of a to the x, you also get x. Now I had boxed this in on the page with inverses as the key point. Here we need to specify more about what these x's are allowed to be. The x's here start out in log x and then get hit by the a. So these are four x's that are in the domain of the log function, log base a of x. But the domain of the log function is the range of the a to the x function. Why is that? Because the log and the a to the x are inverses. The domain of one is the range of the other. But we know what the range of the a to the x function is because we've examined it, and that's 0 to infinity. A to the x is never 0 and always positive. Log base a of a to the x equals x. In this case, the x can be anything that is allowed in a to the x. So this is for x in the domain of a to the x, but the domain of a to the x is everything, all real numbers. Since the domain of a function equals the range of its inverse, that means this is now the range of log base a of x. So by putting together the facts we knew about inverses, together with the two functions here, a to the x and log base a of x, we've got all the basic information. But I know that this is a little bit odd sometimes to get used to. So let me draw you a couple more pictures that I hope will clarify a little bit of this. These are pictures similar to what I did before. Suppose I start with the value x, and I apply the function log base a of box to that value x. And I end up, of course, with log base a of x. And see, there's a place where I might not write the parentheses around x because there's only a single thing there. Then if I go backwards and I apply the function a to the x, or a to the box, the exponential function, I end up with back here a to the log base a of x. Follow this around. X becomes log base a of x and then is exponentiated. And of course, since they're inverses, those are equal. So that's the process that's happening here in one direction. Now we can do this in another direction. Suppose we start with x over here. And first we apply a to the box and end up with a to the x. So that's our first direction. And now we continue, apply backwards log base a of box, and end up with log base a of a to the x, which of course is equal to x because these are inverses. So there you have it, written in both directions. The inverse functions undo each other, and this is sort of the picture you want to have in mind of how they do that. First, let's look at finding domains of the log functions. That's worth a little bit of effort here. Find the domain, or domains. I'll do a couple of problems here. The first one's straightforward. Suppose f of x is equal to log base 2 of 1 minus x. Okay? I would like to know what x's are allowed in there. Well, I know that we want 1 minus x to be greater than 0 because if you recall from the previous page, the domain of the log function is always greater than 0. And so, of course, that means that 1 is greater than x. And so that can be written as x is in the interval from minus 1 to 1. This is x less than 1 after all. And if you like the little graphical picture, here's 1, and we're going everything to the left, not including 1. Okay, that one was fairly straightforward. These can be a little bit trickier. Say, for example, with g of x, the algebra just can be messier. The idea is still simple. Log base 5 of, say, 1 plus x over 1 minus x, where, just to make things easy on ourselves, we'll assume that x is not equal to 1, so there's no division by 0 here. So what do I want here again? The log only operates on things that are positive. So I want 1 plus x over 1 minus x to be greater than 0. That's what I desire. Well, if you remember, this is an inequality with a rational expression in it, and we did these, when we did inequalities, by looking for split points. And here the split points are easy to find. Remember how we got split points? They were where the top or the bottom would go to 0. Here that's easy. That's x equal minus 1 or 1. And even though the bottom point is not allowed, it might split the real number line into places where this is positive and negative, so we need to consider it. And then we can do our little chart, if you recall. I'll make this short and sweet. Minus 1 to 1, and we'll pick an easy number on each side, maybe minus 2, 0 here, and 2. And I'm going to put these numbers directly in the entire expression. So if I put minus 2 in here, 1 plus x over 1 minus x with a minus 2 in it, that's a negative on the top and a positive on the bottom, so it'll be negative overall. The expression here will be, I'll just write box to save me writing, will be equal to 0 here at minus 1. And at 1, however, it's undefined. So this is undefined because that's where we would have division by 0. And in here, we'll do the same kind of operation. What is 1 plus x over 1 minus x here? Putting 0 in for x, I get 1, so that makes this positive. And 1 plus x over 1 minus x, put a 2 in, I get a 3 over a negative. So this is negative. So it looks like the region I want is the region inside here. Not including minus 1 or 1, because that would be equality, and inside where this is greater than 0. So putting this all together, that means x is in the interval from minus 1 to 1, and that is the domain of this function. Again, pictorially, if that's minus 1 and this is 1, it's open there, and everything in between. So there's just a little bit of practice with domains. And here now, let me do a little practice with the use of the log and the exponential as inverses of one another. This is the kind of stuff you want to practice on your own. Suppose you have y equals log base 3 of x. And suppose you want to solve for x. Now we're going to spend time later looking at how to solve logarithmic equations. But the basic idea here is not anything fancy. It is simply you want to undo the log. Well, to undo the log, you use its inverse function, the exponent, to the same base. This is base 3. So I will now, we might say, exponentiate, where I'm going to raise both sides up. So 3 up to the y equals 3 up to the log base 3 of x. So I've raised both sides up by exponentiating with the same base. Now by design, the right-hand side, I have exponentiated and logged to the same base, so I get back x. So I have 3 to the y equals x, and I'm done, because that's all I wanted to do here. Okay, let's try another one that's the opposite of this. Suppose I have 1.2 to the 3 power equals m. And I would like to somehow rewrite this so that I don't have an exponent involved? Well, I can bring this exponent down, this is an exponential function, by changing the base, or rather by using the log function which has the same base as this. So what I like to say is, hit it with a log. Hit it with a log. So it will be log base 1.2 of 1.2 to the 3 power equals log base 1.2 of m. And then this left-hand side, by design, I'm logging and exponentiating, will give me 3. And on the right, I just have what I had before, log of 1.2, and I'll just write m because there's only a single object there. And there you go. Now that was just a little bit of practice. These are the kind of operations you want to do in larger numbers so that you feel confident when these things occur in equations later. Here's another thing that will occur later when we do equations. It's the result of this fact. If you have two exponentials, a to the u equal a to the v, same base, different powers. And remember, of course, I'm talking about a greater than 0, a not equal to 1, as usual. Then the conclusion is that if they have the same base, then the powers must also be the same. I won't prove this, but it's a fact that I think you'll believe. And then I can apply it to an example here, where I can ask the question, find exactly the value of log base 3 of 1/3. Now there's several ways to do this. I want to show you one way just to get this pattern down. If you know enough about logs and powers, you can write this down pretty quickly without any difficulty. But let me just show you how you might do this in general. What you first want to do is set y equal to the object you're looking for. Say y equal log 3 of 1/3. And then what I want to do again is get rid of the log. So I'm going to, because the log is in the way of me seeing what this is exactly, so I'll get rid of the log and hope that I'll be better off. I want to exponentiate then. By what? Exponentiate by the exponential function with base 3. So this will now be 3 to the y again, and 3 to the log base 3 of 1/3. Well, by design, the right-hand side, exponentiation and log, with the same base, leaves me with whatever the x is, which is 1/3. Of course, 1/3 can be written as 3 to the minus 1. So what I have now is 3 to the y equals 3 to the minus 1. And by the fact above, that means that y is equal to minus 1. And if you remember, y was the original expression. So I now know the original expression is equal to minus 1. And I've done what I set out to do. Okay, good. There's a little bit of practice with logs. Now let's look at, say, the graph of the function. Graph of f of x equals log base a of x. Well, you know, I shouldn't have to work at all to do this. Because as I saw in the previous segment, the graph of the inverse of a given function is simply the given function's graph reflected across the y equals x line, the 45-degree line. So since I know the graph of a to the x, I ought to be able to produce this graph without much effort. So let me write that down. All I have to do is reflect the graph of a to the x across the y equals x line. And that's exactly what I've done here in this drawing that I want to show you. Here's the drawing. And I had to do this in two different cases, depending on whether a is greater than 0 and less than 1, or greater than 1. So let's look at this case first. Suppose a is in this interval from 0 to 1. Well, if you remember, the graph of the exponential function looked like a graph that came up from below and came down like this. Well, if you can imagine that being flipped across this line, the part that was low down here becomes high up here. The part that was high up here has been flipped over down here. So this is the graph of the log base a of x when the a is between 0 and 1. And you can see it has all the usual features. 1, 0 is on the graph. A1 is on the graph because A here goes up to 1. And it is a decreasing function. It's going down to infinity. It is going up to infinity in that direction. And clearly the y-axis is a vertical asymptote, the x equals 0 line. And the point A1, now of course that's information we may not have had. We now see that the log of 1 from this, the log of 1 must be 0. We also see that the log of A must be 1. So we've gotten a couple of pieces of facts, a couple of pieces of information from this that comes from simply looking at this as a reflection of a to the x's graph. Let's look at the other one, the case where a is greater than 1. Here's the graph I've drawn for this. In this case, a is greater than 1. So the original graph it started low down here, passed through 1, and went on to infinity. Now reflecting it across the y equals x line, we end up with a graph that looks something like this. This is an increasing graph, goes off to infinity here, goes down to minus infinity here, passes through 1 as the other one did, so that the point 1, 0 is on the graph, and then the point A1 is also on the graph. And of course the y-axis once again has become a vertical asymptote because for the original exponential function the x-axis was a horizontal asymptote, and now they have switched places upon reflection around y equals x. So this is the graph of the log base a where the a is greater than 1. Okay. Well, let's put all this together into a summary about logarithmic functions. Now here's the summary I have for you. And this is very reminiscent of the one I had for exponential functions. It should remind you of it. Logarithmic functions base a. Here's the way it looks. Log base a of x. That a is a subscript. The a's will come either from 0 to 1 or above 1. The domain is 0 to infinity. The domain of any log function is always only positive numbers. The range is everything. That was the up and down range. X-intercept is 1, 0 instead of the 0, 1 we had for exponential. There are no y-intercepts. The vertical asymptote, x equals 0, is now the vertical line, which is the y-axis. F is 1 to 1 because the original function was 1 to 1. The original a to the x function was 1 to 1. And it passes through A1. For a between 0 and 1, the graph looks like this without all of the extraneous notes. It is a decreasing function. And if a is greater than 1, it's an increasing function. It looks like this. And both of these you see have y as a vertical asymptote. So, with all of this information, it's time for you to try a problem. And here's one I will pose to you. I want you to graph this problem. Graph the function f of x equals minus log base 2 of x plus 1. Now, I don't think you'll have any difficulty with it, but I'll come back in a minute and show you what I did. All right, here's the function that I wanted you to graph. Should be fairly straightforward. We'll start out, and I'm going to do this by hand because it is easy to look at. We'll start off with what might be called the core function here, log base 2 of x. Ignoring the shift here and this reflection, just take log base 2 of x. Now since the 2 is bigger than 1, I know what the picture of this has to look like. The picture of this has to look like the following. Here is my axes. Now remember, if this were the exponential would go up like this. I'll just dot it in because I don't want that now. That would be the exponential if this were 2 to the x. Okay? What we want is what happens when you reflect it around, so the reflection gives me a picture something like this, passing through 1. So that's a way to remember this in case you've forgotten what it might look like. Okay. Let's go over to the right, and the next thing we want to look at is log base 2 of x plus 1. Now what is that? That's a horizontal, you remember, leftward by 1. So this picture will shift leftward. So I will have this, and the 1 is struck here at 1. It will now strike at the origin. So it will have the line minus 1 here as its asymptote, and it will do something like this, striking here at 0 now. So that is the picture that I have for log base 2 of x plus 1. And what's left? The negative, which we know is going to be, I'll put that down here. This is minus log base 2 of x plus 1. And the minus will do what? Well, it's taking the y value and negating it. And this is the final function here. So it's going to reflect this around the x-axis. So my picture will be something like this. There's my y and my x-axis. And this, the reflection around the x-axis will not change this asymptote, so it'll still stay there at minus 1. But now instead of coming from above and going to the right like that, it'll now have this shape, more or less. And that will be the graph that we were looking for in this function. So, I hope you ended up with that yourself. That should be roughly the same kind of picture that you've got on your screen. And this passes again through 0. Okay, I think that's all I'm going to say about that one. Let me just for the record show you one more. You can see another graph here. Suppose we look at g of x equals log 1/3 base of minus x plus 1. Solution by hand will be the following. The first picture will be log base 1/3 of x. Seems the natural thing to do. And again, here is how you might remember the picture in case you've forgotten it. The picture, the original exponential function would look something like that. 1/3 to the x would look something like that. We're now flipping that across the y equals x line, so now we have a graph that looks like this. Asymptotic to the y-axis and coming down and going to infinity, passing here at 1. Okay. Let's see what we can do next. We probably want to look at log base 1/3 of minus x next. Now since the minus is inside, we're talking about a reflection across the y-axis this time. So the picture will look pretty easy to draw, just like that, hitting here at minus 1 now. There's y and there's x. And we've flipped it across the y-axis. Finally, we have the plus 1, and we know what that will do. That will simply shift everything up vertically. So let me move that down here. And we'll have log base 1/3 minus x plus 1. That's the function g of x. That's what we were trying to get to. And as I said, it will be simply shifted upward. So see if I can draw that. This had passed at minus 1. So now it's going to pass here at this point, which is right above minus 1, but at a height of 1. And it will still be asymptotic, so it looks something like that. Passing through this point here, which will be what? Minus 1, 1 will be that point. So I've given you a couple of landmarks, and that gives you a rough idea of what this graph will look like in the end. So on that, we'll stop, and then we'll come back and talk about a special base, the base e, which gives us, as you might expect, the natural logarithmic function. All right, now we'll look at the analog to the natural exponential function, the natural logarithmic function. Its inverse, as you might expect. So here we go. Definition, get right to it. The natural logarithmic function, is the function we denote by f of x equals log base e of x, where the base is, of course, the number e that we examined earlier. Now that would be what you expect me to write. However, no one writes the log base e function this way, except to make the point that it's the inverse of e to the x. However, it is always denoted, and this is the way I will use it from now on, and so should you. F of x equals log of x that way, where I'm using an L and an N. And where does this come from? Well, n stands for log, L stands for log, and n stands for natural, as you might expect. So this is the notation I want you to use from now on for the natural logarithmic function. Do not use log base e of x. I just wrote that here to make the point that it is the inverse of the e to the x function. But this is the notation you'll use from now on. So, as I said, since these are inverses, so we know that the natural log of e to the x will be equal to x, and e to the natural log of x will be equal to x also. This is the same pattern we've seen before, except that now it's with these very important functions, the natural log and the natural exponential functions. Now what do these hold for? Well, the first one, e to the x can be anything. So this holds for all x in the real numbers, and that is the domain of e to the x. And here it holds for all x's that are allowed in the log, because the log is where the x's begin. This is for x in the interval from 0 to infinity. Only positive numbers, and that's the domain, of course, of the natural log of x. So what we're seeing here are the facts about inverses that we've seen before. So there's nothing new here. I might make a couple of remarks. One is use the lnx whenever possible. And really that goes for e to the x also. Everything you do with logs and exponential functions can be turned into these two functions, e to the x or natural log of x. And that makes your work of memorizing things much easier if you know the trick to change everything into natural log or natural exponential. The second remark I wanted to make here is about your calculator keys. On your calculator, there will be keys that look like this, ln key. There will also be an log key. Now be very careful that you consider that these are two different keys for two different reasons, for a given reason. Natural log has base e. Log is considered base 10. The first is called natural. The second is called common logarithms. Now we're going to spend some time talking about these in a little bit, but I wanted to make sure that you're aware on your calculator to always use the ln key when you want base e. And log will be base 10. And for any other base, we'll find out how to deal with that in a moment. So I'll come back.